In our intuition, time is an independently existing abstract concept with a single direction, steadily flowing from the past to the future. But have you ever wondered why this is the case? Why can time only move forward and not backward? Why can we only remember the past and not the future? Do we exist within time, or does time exist within us? Today, we're going to explore a book called The Order of Time Star. This book will take us on a journey to uncover the essence of time, challenging our ingrained perceptions of it. The author, Carlo Rovelli, is an Italian physicist and one of the pioneers of loop quantum gravity theory. He's been hailed as the next Stephen Hawking. This book is Rovelli's latest work and was named one of Time magazine's top 10 non-fiction books of 2018. Benedict Cumberbatch, who played Doctor Strange in the Marvel film Doctor Strange *, recorded the audiobook version, which won the UK National Book Award. We'll break down this book into 3 parts. First, we'll explore the truth about time from both macroscopic and microscopic perspectives. Second, we'll step into a world without time and see how everything operates without its guidance. Third, we'll investigate why, in a world where time doesn't exist, we can still distinctly feel its presence. Let's embark on this journey to uncover the truth about time. The truth about time from macroscopic and microscopic perspectives. Let's start by re-examining time to seek its true nature. From a macroscopic perspective, our intuitive sense of time suggests it has 4 key characteristics: independence, uniformity, immediacy, and directionality. However, recent findings in physics have overturned these notions. Let's begin with independence. People generally believe time operates autonomously, unstoppable by any force. This idea originates with Newton. Newton posited that time is absolutely independent, unaffected by external entities. He built the foundations of modern physics on this view of time, which we've long accepted as common sense. But in reality, the notion that time runs independently and irresistibly is merely Newton's personal perspective. It's not an innate human intuition. Some philosophers have opposed this view. The ancient Greek philosopher Aristotle, for instance, was a notable dissenter. Known as the first person to ask, "What is time?" Nearly 2 millennia before Newton, Aristotle argued that time is a measure of change. In other words, when we talk about time, we're actually referring to things that change. For example, if I say I'm going on a 3-day business trip, those 3 days simply mean the sun will cycle across the sky 3 times between my departure and return. That's it. So, if everything remained unchanged, would time stop flowing? Aristotle's answer is yes. If nothing changes, time ceases to exist because time is merely a record of change. If that's the case, why can we still feel time passing even when we lie still in the pitch-black silence of night with our eyes closed? It's because your heart is beating, and your thoughts are shifting, so you still perceive time. This view, that time depends on change to exist, stands in stark contrast to Newton's. Another contemporary of Newton, the German mathematician Leibniz, also opposed him. Leibniz argued that time cannot exist independently. Behind time lies something more fundamental: causality. For instance, consider a glass of beer on the table. It's steeped in causal relationships. If you don't open the bottle, the beer can't be poured. If you don't pour it, the glass won't fill. By tracing these causal links, we can discern the temporal sequence of events. To Leibniz, time is like a chain of dominoes, a sequence of causal transmissions. The first domino falls, affecting the second, which then impacts the third, and so on. As we perceive this transfer of causality, we experience the passage of time. Leibniz staunchly defended this view, so much so that, according to legend, he removed the letter T from his name. In Newtonian physics, T represents time, but Leibniz rejected Newton's absolute T as non-existent, aligning his name with his belief. So, is time truly independent? Einstein delivered the final verdict: time is not independent. Let's see how he proved it. First, Einstein established the principle of the invariance of the speed of light, meaning light travels at the same speed for all observers, whether you're stationary or aboard a spaceship. According to special relativity, exceeding the speed of light is impossible, indirectly supporting Leibniz's view. Why? Imagine someone across from you sends a faster-than-light message with their phone. You'd receive it before seeing them even reach for their device. This disrupts causality. If superluminal events were allowed, absurd scenarios would emerge, a glass shattering before it hits the ground, a victim dying before the gun is fired, and so forth. Thus, special relativity's invariant light speed ensures causality remains intact, reinforcing Leibniz's perspective. Second, Einstein introduced a new concept of spacetime. Since light speed is constant and the universe is vast, light takes time to travel from one point to another. The greater the distance, the longer the delay, showing that time and space are inseparable. A clear example is the light year, a unit of distance defined by time, implying their indivisibility. Einstein unified them into space-time. He also integrated gravity into this framework. For instance, the Sun's gravity causes Earth to orbit, but this is really the Sun's immense mass warping nearby space, with Earth sliding along the curved path. This spatial curvature acts as a gravitational field. Since space and time are two sides of the same coin, spacetime is the gravitational field, and the gravitational field is spacetime. A field is a physical entity, like the electromagnetic field. Though independent of us, it's not detached from matter, it's dynamic and tied to change. In Newton's view, time is like a stage, with life and matter as actors performing upon it. Regardless of their actions, the stage remains static. But in Einstein's view, the stage performs alongside the actors, adapting to their movements. Time's absolute independence crumbles. How exactly does this temporal stage perform? That brings us to time's second characteristic, uniformity. People commonly assume time is uniform, that it's equal for everyone, flowing at a steady, universal pace. But the reality is quite the opposite. Time is never fair. Its true nature is variable, speeding up or slowing down. Two factors influence this, mass and velocity. First, mass. Objects slow time around them, with greater mass causing more pronounced slowing. This occurs because massive objects warp spacetime through gravity. The more massive, the greater the distortion. Earth, a colossal entity, slows time more near its core. Thus, people on plains age more slowly than those on mountaintops, even if the altitude difference is mere centimeters. Your feet cells age slightly slower than those in your head. Next, velocity. Motion also slows time. Time on a high-speed train lags behind time on a bicycle. The faster the motion, the slower the time. Why? Consider an experiment with a photon clock, two mirrors, one above the other, with a photon bouncing vertically between them. Its round trips measure time. On the ground, with the mirrors 1 meter apart, the photon completes about 150 million round trips per second. Now place this clock on a speeding spaceship. To those aboard, the photon still bounces vertically. But to an observer outside, the photon's path combines its vertical motion with the ship's forward motion, tracing a diagonal. Since light speed is constant, a longer path means more time per trip. Thus, to you, time on the spaceship slows, everything unfolds in slow motion. A sneeze taking 1 second aboard might appear to take a minute from outside. We now know mass and velocity alter time's flow. People at different altitudes or on different vehicles experience distinct timelines. So, which time is real? The book suggests there are many times, none inherently truer than another, overturning time's second characteristic, uniformity. If two people experience different timelines, how do they communicate? This leads us to time's third characteristic, immediacy. A key concept in time is now. If your family is in the room and you want to know what they're doing now, you look at them. But what you see is light traveling from them to your eyes, taking a tiny fraction of a second, say, a few nanoseconds. You're not seeing now, but a few nanoseconds ago. Normally, we ignore this delay. But if your family lived on Proxima Centauri, for light years away, you'd see what they did for years ago, not now. You might think, what I see for years later is what they're doing now, right? Not quite. As we've established, time isn't uniform across the universe. For years on Earth might be 10 or 15 years for them. Asking which moment on Proxima Centauri corresponds to Earth's now is meaningless, like asking which team won a basketball championship without context. No single moment there aligns with our now. Beyond Proxima Centauri, the universe lacks a unified time, its temporality is local. Earth's now is a bubble around us, never extending universally. How far does this bubble reach? It depends on our precision. The more precise, the smaller the bubble. With nanoseconds, now spans meters, with milliseconds, thousands of kilometers. Since humans can't discern fractions of a second, we treat Earth as one bubble. Now is a fuzzy construct born of our perception, like seeing a rainbow intersect a forest from afar, only to find no intersection up close. For daily life, these traits aren't the most impactful. What we find most relentless is time's fourth characteristic, directionality. For centuries, countless people have lamented time's one-way flow. Why does it distinguish past from future? 19th and 20th century physics grappled with this. While we take time's forward march as obvious, no physical law or equation definitively separates past from future. Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, and Heisenberg and Schrödinger's quantum mechanics describe reversible phenomena. A planet's future position and velocity can be calculated forward or backward. If both directions work, why call one past and the other future? Only one physical law is irreversible, the second law of thermodynamics. It states heat flows from hotter to cooler objects, never the reverse, the sole unidirectional law in physics. Heat closely ties to time's directionality. Anything distinguishing past from future involves heat. A stone hitting the ground converts mechanical energy to heat, warming the Earth slightly as the heat dissipates and motion ceases. Without heat, energy conservation would keep it bouncing forever. Aging involves bodily heat, a bike wears out from frictional heat, thinking generates heat in the brain. Every temporal process involves heat. As the only physical variable tied to irreversibility, heat embodies time. How does it distinguish past from future? If the universe began in thermal equilibrium, uniform temperature everywhere, with no change, wouldn't time cease? The answer lies within us, in our blurry, incomplete observation of the world. Consider a deck of cards, the first 26 red, the next 26 black. We'd call this ordered, special. Shuffle it, and suppose it lands in a sequence of clubs, diamonds, spades, hearts. Isn't that another order? Viewing all details, every arrangement is unique, equally ordered. We see the universe similarly, as a vast deck of cards. Earth is a speck, interacting with only a tiny fraction of it. Like blind men feeling an elephant, we perceive a sliver, ignoring the rest, and assume time flows from past to future, feeling its passage. But if we accounted for every cosmic detail, no arrangement would be more ordered or special. Would time's flow vanish? Yes. Time's direction isn't absolute, past and future blur if all details are equal. Thus, time's flow may not be a cosmic trait but a product of our unique human perspective. In the macroscopic world, time lacks independence, uniformity, immediacy, and directionality. Our familiar time is unrecognizable. In the microscopic quantum realm, time's continuity and certainty also falter. We've said spacetime is a gravitational field, a physical entity exhibiting quantum traits at small scales. Quantum systems are discrete, energy changes in specific increments, not continuously. When time is quantized, what happens? Measuring an infinitesimally short duration with the finest clock reveals time isn't smooth but jumps discretely, like a kangaroo, from one value to another. Continuity vanishes. Stranger still, quantum mechanics features uncertainty and superposition. You may know Schrödinger's cat, a thought experiment about superposition. A cat is sealed with radioactive radium and cyanide. If the radium decays, it triggers the cyanide, killing the cat. If not, the cat lives. Quantum theory says the radium is in a superposition of decayed and undecayed states, so the cat is both dead and alive until observed. If time is in superposition, an event can exist in both past and future simultaneously. Hard to fathom, but that's the quantum world. Through macroscopic and microscopic lenses, time loses its familiar traits, nearly vanishing. A world without time. How would the world function without time's guidance? In Part 2, we explore a timeless world. In 1967, two American physicists discovered a foundational equation of quantum gravity that, astonishingly, excludes time. Time vanished. Initially, no one, not even the discoverers, could grasp it. Without time, is the world static? No. The absence of time in the equation doesn't mean stasis, it means change is ubiquitous, independent of time's oversight. It describes not how things change in time but how they change relative to each other. An example clarifies this. Galileo used his pulse to measure a chandelier's swing. Later, since each swing was consistent, the pendulum clock was invented. Doctors then used pendulums to measure patients' pulses. Notice the cycle: Galileo measured pendulums with pulses, doctors measured pulses with pendulums. Time is just an intermediary, we never measure time itself, only physical variables like pulses and swings, relating their changes. Time is like an auxiliary line in geometry, non-existent yet useful. If we find synchronized variables, like pendulums and pulses, we can express time through their mutual changes without designating one as time. Discarding time clarifies that the universe comprises changing events, not static objects. A stone isn't an object but a complex vibration of quantum fields. A cloud isn't an object but condensed water vapor. A family isn't an object but a web of relationships, events, and emotions. A person isn't an object but a dynamic process of food, information, and language flowing in and out. In this universe of shifting events, anything can play time's role, that's how our world truly operates. But if the world lacks time, why do we vividly feel it? Where does it come from? Why time exists? In Part 3, we explore time's origin. Time stems from memory. Heat, as we've said, plays time's role, leaving traces. Writing heats paper slightly via friction, leaving marks. We judge time by traces, the past has them, the future doesn't. In a heatless world, a pen couldn't mark paper, and time would be unjudgeable. Our brains collect past traces into memories, and weave them to predict the future. When someone tosses you an object, your hand moves to where it'll land, guided by past impressions. The brain tells us planting seeds yields crops, or rain wets us outdoors. Seeing a cup fall and shatter, we don't perceive three distinct signals, but one continuous event, not isolated instants but a process. It's like hearing music, we perceive the interplay of notes, not isolated sounds. Without connecting them, we'd hear no melody in the moment. Thus, time is a coherent sensation our brain constructs. This idea is ancient. In Confessions*, the Roman thinker Augustine probed time's essence, saying, "When I measure time, I measure what exists in my mind now, time resides within us." German philosophers Kant and Heidegger agreed, viewing time as a human construct shaped by inner perception. Writer Marcel Proust saw it more keenly, writing in In Search of Lost Time*, that reality consists solely of memory. We've now uncovered time's truth. To summarize, the 6 traits we attribute to time don't exist. First, time isn't independent but tied to change. Second, its flow varies with mass and velocity, people at different altitudes or speeds experience different times. Third, it lacks immediacy, our now may be another's past or future. Fourth, its past to future flow may be a human perspective. Fifth, in the quantum realm, time isn't continuous. Sixth, there, it loses certainty, with events coexisting in past and future. Next, we entered a timeless world, learning all objects, like clouds or stones, are events in flux. Finally, exploring memory, we found time is a continuous sensation our brain creates. In 1955, upon a dear friend's death, Einstein said, "He's left this world a step ahead of me, but it's no matter." For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. This wasn't academic but a reflection on life, deeper than physics. Time arises because of us, we are its creators. That concludes our exploration of asterisk the order of time star. If you found this video fascinating, please like, comment, and subscribe to our channel.